This week's topic is water resources. We're going to start with kind of the basics here, which is the water cycle. Hopefully, you're all familiar with the water cycle. You probably learned about it way back in grade school, and it's been brought up several different times. But this is the movement of water through the Earth's system. So, everything from groundwater flow to surface water in the ocean and rivers to evaporation, which takes water into the atmosphere and rain, which brings it back down to Earth. This system is driven by energy from the sun. So when we break it down into some numbers, we can see where the water is. And this is a useful chart. It's in your textbook. But a key thing that a lot of people miss is the right-hand column and the importance of the right-hand column, because the right-hand column tells you something about how the water is moving through the system. So, for example, there's a lot of water in the oceans. It tends to stay there for quite a while. If we look at fresh water, you'll notice our largest freshwater supply is actually tied up in ice caps and glaciers. And you'll notice that it stays in that part of the water cycle, again, for a very long time. Groundwater as well, which is a significant source of our water supply, also has a long residence time. On the other hand, things like the atmosphere and rivers and streams have very short residence times. Now you'll notice the total volume here looks kind of small, but with these short residence times, if you multiply this, 9 days is a little more than a week. If you multiply this number by 52, that'll give you an idea of how much water is available in the atmosphere over the course of a year. If you multiply this number by 25, because it's 2-week residence time, you'll get a much bigger number, and that's how much water is available in rivers and streams over the course of a year. So that takes us to this picture, which is our water budget. You'll notice that evaporating into the atmosphere is 505 cubic kilometers plus 72. So that's over the course of a year. So we can see that high volume of water available in the atmosphere. And you'll notice in the runoff as well, we've got 47,000 cubic kilometers. So some of these numbers go up if you're looking at an annual budget because they have such a short residence time. So let's take a look at where the water is, where we can access it. Unfortunately, we don't really have the option of collecting water from the ice caps. Most of that frozen water is on Greenland and Antarctica. It's just too far away to even collect. So our water supplies will come primarily from surface water and groundwater. Surface water we've already talked about with respect to floods, and so the factors are pretty much the same here when we look at surface water. Supply factors include the amount of precipitation we get, the geology of the ground that underlies your drainage basin or your what's also called a watershed, the shape, the relief, orientation to storms, vegetation. All of those things are going to help determine how much water is available in a surface water supply system. So we're going to kind of leave that aside and focus on groundwater recharge. The one thing I'll mention before we move on, though, is that there are two ways to develop this surface water supply. One way is to just stick a pipe in the stream and pump the water out. The one issue that can come up with that is if your river or stream is seasonally has a lot of variation. Very often a dam is built to create a reservoir, and then the water is taken out of the reservoir. The city of Streator, for example, has a reservoir off to the side of the Vermilion River, and then they have a little dam in the river. They collect water from the river, they pump it into their lake, and then that's their storage. So what we're going to do on the rest of this little video is talk about groundwater, and that's where our focus is going to be in lab as well, because it's hidden and it needs more explanation and more discussion so that you can understand what's going on there. Groundwater is not a magical supply. Its ultimate source comes from precipitation. So if you don't get a lot of rain, there might be a lot of water available in the ground, but if you start pumping it out very quickly, uh, it's not being replaced because it's the rain that replaces that. So we'll talk about sustainability, or you want to think about sustainability when it comes to groundwater. And recharge is what sustains your groundwater supply. The other place where you sometimes get water going into the ground is out of the banks of a stream or a lake, but that actually is what you would find in a desert area. In our area, groundwater actually discharges or seeps into the bottom of the Illinois River and seeps into the bottom of local lakes and streams. And so groundwater is actually lost to surface water. So let's take a look at groundwater distribution on this next slide. This is a picture out of your book. It gives us some of our terminology. The area above what's labeled as the water table here, most of the pore spaces are filled with air, and it is called the vadose zone. It is also called the zone of aeration. So it actually has several names. So zone of aeration and vadose zone. Below the water table, all of the pore spaces are filled with water. And so this is called the zone of saturation or the saturated zone. The area above is also called the unsaturated zone. So it has three names: zone of aeration, vadose zone, unsaturated zone. And I apologize if I switch around the use of those. And then the boundary between the two is called the water table. One thing to know about the water table is that it is not static. It does not stay in the same place. If you add water from rain, so recharge would fall on the ground here. If you add some rain, the water table can rise. If it stops raining, you'll notice that the groundwater moves into the banks of this stream and leaves the system. Over time, the water table can fall. And it's pretty common for the water table to rise in the wet season, whatever that happens to be, and then fall in the dry season. So if I look in the well that's next to my house in the spring, after we get a lot of rain, the water in that well is just going to be a few feet below the surface. If I go out and look there now, I'm guessing it's probably somewhere in the neighborhood of 15 to 20 feet below the ground surface. So it can vary quite a bit over the course of a year. So those are the names of some of the things. We got a few more names to take a look at. We have the term aquifer. An aquifer refers to a unit of geologic materials that allows the groundwater to move freely. Now that's kind of a vague definition, and we'll talk about why that is. The other definition, which was given to me in college by my groundwater professor, was an aquifer is a unit that yields enough water. Again, kind of a vague definition. How much is enough? Well, if you're this house right here, enough water is maybe a few hundred gallons a day. If you're a city, like the city of La Salle or Peru, you might need several million gallons a day. And so the definition of the aquifer actually can vary with the user. So people who use a lot of water need a one that transmits water very quickly in order for them to consider it as an aquifer. An aquitard is a geologic unit that retards the flow of groundwater. It's not the groundwater doesn't go through it. It goes through it very, very, very slowly. And this would be like a layer of clay. And we'll take a look at these in lab next week. This week we have a groundwater model, and we can talk a little bit more about the difference between aquifers and aquitards. The term aquiclude used to be used quite a bit. I don't see it as much anymore. It implies that groundwater is precluded or won't flow through the material, which is very unusual. Much more typical is it just flows through very, very slowly. So let's take a look at the next slide. The confining layers here are aquatards. They're probably made of a substance like clay that water doesn't flow through very easily. You can see where our water table is in our recharge zone. We have two aquifers here. One is unconfined. It has the water table as the top of the aquifer. And if you add water, the water table will go up. And in the dry time of the year, it will go down. So that's an unconfined aquifer. A confined aquifer, if you add water to that, you'll notice the top can't go up. So what happens is the water ends up being under pressure. And the more water you add, the higher the pressure will be. And if you take water out, you will lower the pressure in that aquifer. And it shows also this effluent stream. I would call it a gaining stream. It's gaining water from the ground. You'll notice there's a spring here where the water table comes into contact with the surface. And a spring is just a term that we use for saying the water is coming out of the ground in that location. And this diagram just kind of shows you how you can build up pressure in a confined aquifer. And if you drill down into that aquifer, if there's enough pressure, water can flow out of that well. And you'll notice a dotted line up here in the air. That is what's called the pressure surface. That's a measure of how much pressure is in that confined aquifer. The implication of that dotted line is that if you drilled a well right here, directly below that line, the water in the well could rise up as high as that dotted line. So that's the pressure surface. And when we get into lab, we'll talk more about the importance of pressure surface rather than talking about the water table, because it impacts how the groundwater flows. And we'll even take a look at that on a slide in a minute. So where the groundwater comes out of the ground on its own, we usually call it a spring. So we might say there is a spring-fed creek or just an open spring like this where the water's pouring out. The Illinois River, for example, is an effluent stream or a spring-fed river where water is actually flowing into the banks of the Illinois River. That provides what we call base flow, which means that the Illinois River it just always has water in it, and a lot of that water is coming out of the ground. The other way to get some groundwater discharge is to drill a hole in the ground and pump the water out, and that's a well. So in lab, we're going to spend some time calculating groundwater flow. So I'll just put the equation up here so you can see it. If you watch this, you'll be able to answer some of the questions I ask in lab. This is called Darcy's Law. Q equals KIA. Well, what does that mean? Well, Q is discharge. It's the volume of water over time. And the rest of the equation tells us what controls that flow. So you might think, what determines how fast water flows in the ground? It's flowing through sand. One of the factors would be what we call hydraulic conductivity. It's how connected are the pore spaces in that sand, and that is a property that we call permeability. Connected pore spaces lead to a high permeability. If you have pore spaces that are not connected, then you have low permeability. So the next factor is the hydraulic gradient. That is the slope of the pressure surface in that groundwater system. And so if it's an unconfined aquifer, the pressure surface is the water table. If it's a confined aquifer, the pressure surface is however high the water would go if you drill the well into that aquifer. So if we look at the difference in that pressure surface over a certain distance on the land, so if we go from, say, here to here, you can see the pressure surface has a slope. That tells us two things. It tells us the direction of groundwater flow and the speed.